Questo me l'ha chiuso, no?
Sì, sì. Io parlo di lì. Uso quello.
Sì, però c'è un E. Secondo me perché anche questo.
Per spegnere il suo.
Ah, ok.
No, niente.
Suo è aspetta. No, but it's because your audio is on. Like sound. Because it goes into the.
Yes, yes, you equal charge.
Yeah, exactly.
Yes, you're done.
Okay, so good afternoon, everyone. It's a pleasure to introduce Ravi, so you might have seen around. So he's been here for a while. He's here for another week or so, more or less. We met 15 years ago, I think now, when I was doing my master's thesis in Padova, and he was already in Penn, or he was visiting ICTP. So Ravi did his PhD in Cambridge and then moved to Berkeley and then to MPA in Munich. And I checked the dates today, so we were there exactly 20 years apart. And despite this, we still managed to gossip about the same people. So it is remarkable. And then he was in Fermilab too, and then become a professor in Pittsburgh, and now in Pennsylvania. So he's expert in cosmology and structure formation and statistical approach in general to structure formation. So you will hear today about cosmology and Bay.
Thanks, Julia. It's great to be here. It's been great to be in Bologna. Thanks a lot for the invitation. It's been just fantastic. Yeah. So I was going to talk about the cosmic web and some of the cosmology we do with this Baryon Acoustic Oscillation that we see in the distribution of galaxies. And so at the start of my stay here, I did a mini course, or I did the first part of a mini course on structure formation. And in that, I promised to talk about the physics that makes the BAO. So the first few slides will be trying to set that, yeah, because I didn't end up doing it in the course. Yeah. And so the first part will be setting that up, and then the second part will be some of the results. Okay. Most of this is work done with or done by Farnik, who is a PhD student, now a postdoc at Yale, who's now working with Nikhil Padmanabhan. Some of the stuff was developed by Roya and Bruno, and then Asim and I have been extending some of that. And if I have time, I'll talk about stuff with Marcello that's associated to stuff that we've done along with Julian. Okay, so I first talked about the motivation of why we think the BAO Baryon Acoustics Oscillation signal is useful, and then I'll talk about how we actually try to estimate it. So the quick background is there's the CMB. The CMB is early times. The photons are very energetic. They can keep the hydrogen ionized. The universe expands. As the universe expands, the photons cool. They lose energy. They can no longer keep the hydrogen ionized. And so at that point, the photons, from scattering off of the free electrons, so not traveling in a straight line in the universe, from the time the universe become cool enough, are able to travel in a straight line because they no longer scatter off of photons. So that's illustrated here. The photons are scattering, scattering, scattering. The universe gets cool, and they can travel in a straight line. Okay. What's shown here is what if the universe had one plane wave where there was a region that was dense, underdense, dense, underdense, dense, underdense, stripes, okay? And so, so dense means hot, underdense means less hot. The photons just bounce until it's too cool, and then the photons go in a straight line, okay? And what this is trying to show you is that's happening in 3D, but what happens in 2D? What do we see in 2D? So imagine that we are an observer at the center, and we receive light, when the universe is young from close to us, and when the universe is old from further and further and further away. And so what the expanding circle is showing you is that we receive light from further and further and further away. So initially, the light that we will see, as soon as the photons are able to travel in a straight line, will all be from a local region around us. So the whole sky will have the same temperature. But as you wait, you will get light from further and further and further away. And so you will see more and more of the striped pattern. And so you will see on your sky, you will see a range of temperatures. Okay? And that's how the physics in 3D gets imprinted into a pattern in 2D on the sky. And you can see that there will be, from the shell, you will see that there will be, light, dark, light, dark, light, dark pattern in the sky. Now, in reality, the initial fluctuations was not just one wave, it was many waves of many wavelengths in many different directions. Okay, but the fundamental idea is this, that you will have a pattern imprinted on the skies that has to do with the fluctuations of the early universe at the time the CMB was created, meaning the photons were left to travel in a straight line. Okay, so that's the physics. And so because of that, because we know what this time, because we know that this pattern will be imprinted in the sky, the sizes of the spots will have to do with the sizes of the spots and the physical size of the spots and how far they are from us. And so if they are 14 billion light years away from us, they will have a certain angular size. But what that angular size is will depend on the curvature of the universe. And so we can make some estimate of the curvature of the universe if we know the physics of the spots, and we have an estimate as well of how far they are from us. And so that's the game that people play with the CMB. They are essentially measuring the sizes of the angular sizes of the spots, and we have an idea of the physics that made the spots, so we know their physical size, and so we can put a constraint on the curvature of the universe. Okay, and so that's the CMB. And so now the question is, the CMB is a picture of what the universe was like when it was about 3,000 degrees hot, about age of about 400,000 years. And the question is, can we use this same physics to learn not just about how far the surface of last scattering is from us, but the subsequent expansion of the universe since that time? Okay. And so the idea is, can we use the same physics, not just at that time, 14 billion years ago, but also since then? Yeah. And so the idea is the following, that the photons, they were pushing against the electrons, and so they were pushing against baryons. So they were coupled to the baryons, and this is trying to illustrate if you had an overdensity initially of photons and of baryons and of non-baryonic matter, the photons will go out from a hot region towards cool. As they go out, they will push the electrons. As they push the electrons, they will drag also the rest of the baryonic matter, and you will make a shell that gets pushed further and further out for 400,000 years. Then the photons stop pushing because the universe became cool enough. And so now you will just have this shell. You will still have this spike of any matter that is not interacting with the photons. If the universe is filled with dark matter, there will still be this spike in the center. But the baryons will have gone a little bit further away. And then in the 14 billion years, from that time, the baryons might start to move around and they might try to come back towards the center. Okay? Because of gravity now. Yeah, so 14 billion years ago, they were all pushed out, a shell was made, and now gravity will go to work. So that's the idea. And of course, again, this was the simple picture. In reality, we don't have one shell, we have a whole set of shells. Okay. So on the slide here, I put an estimate of the size of one shell. Yeah? And so I said, basically, you're moving for about 400,000 years at more or less the speed of light, by an amount that depends on how many baryons there are and how many photons push the baryons. And so that gives some scale. That turns out to be about 130 kiloparsecs. That was at a redshift of 1,000, and the CMB was made. And so roughly stretched by a factor of 1,000 to 140 megaparsecs. Okay. So that's the radius of this shell today should be about 140 megaparsecs. Okay. And of course, there's many of these shells, right? Because there were many different peaks, each of them pushing the baryons away until they were released. And so the question is, from this mess, buried in this mess, is this scale 140 megaparsecs today? So the way you would do it is you would go to each peak and you would count and you would see if there was an excess of baryons at 145 megaparsecs around each of these peaks. So that's what you would try to do. Now, so this is the cartoon, right? You go to each peak because those baryons have now made stars in the 14 billion years since the CMB. So you sit on the stars, or you sit on the galaxies, and you count the excess galaxies around you. And you're looking for a feature on this scale, 140 megaparsecs. Okay, so that's the same physics as the CMB, because the radius of the shell is set by the same physics that made the spots. But now that circle can, the radius of that circle is 140 moving megaparsecs, but if it's close to us, it's one angular size. If it's far from us, it's another angular size. And so we can map out the expansion of the universe by measuring the angular size of this thing as a function of distance from us. So it's like a geometrical test, a geometrical measurement of the expansion history of the universe. So because you can use the same physics, it's not only the geometrical test at the surface of last scattering, but at every time since then, where you have enough galaxies to make this measurement. So that's called the BAO feature, okay? And we think of, so just like we think of the spots as being a standard rod whose angular size we can use to do geometry, so too now the distribution of galaxies has embedded in it this standard rod, okay, to do geometry. A little bit of detail here, more detail than we want for this talk. I've given the equations, but the idea is simply, if I'm an observer and I'm looking at these circles on the sky, okay, the circles on the sky, this is very idealized, right? These are circles on the sky of a fixed angular size, because I'm assuming that all my galaxies are at one redshift. If they're all at one redshift, I will get one radius on the sky. And now I can ask if I'm making a measurement across the line of sight, that's the angular diameter distance relation, or I'm making a measurement along the line of sight, that's just the Hubble expansion. And so this circle will be some combination of along the line of sight and across the line of sight. Okay, and the point of these things in boxes, the formula in boxes, just to say that in the standard model, we have expressions for these things. So we know how distances across and along the line of sight will appear in this. So how we will map the angular size that we see and the distance in redshift that we see into 140 megaparsecs. Okay, and so that means we can start trying to, so we can do cosmology with this. The thing we do cosmology with for the purpose of this talk is we just make this combination of two distances across the line of sight, one along the line of sight, that's 3D, and then we just take the cube root of that. Right? So that's the distance estimate that we'll be using. Okay. So in practice, what do we do? In practice, because it's more complicated, right? We have galaxies at a range of redshift. So what you do is you select galaxies in one redshift, you play this game. You select galaxies in another redshift, you play this game, and so on. And so one issue is that you select galaxies at some redshift, and they have some angular distribution on the sky. But what you're going to do is you're going to convert angles and redshifts into distances. And to do that, you have to assume a cosmology. And so we assume the cosmology that is given to us by the Planck satellite. We make the conversion. If that conversion is wrong, then we will not get the same distance along the line of sight as across for these circles. It will only be if we have the right cosmology that this will work. Okay, and so that's the game that's played, right? It turns out that the Planck cosmology gives you close enough to these nice round circles that this is not a significant source of error, right, to play this game. Okay. And so once you've done that, you have a nice circle. Then you measure the radius of this circle. And if the radius is 145 megaparsecs, you say, I have a self-consistent story. If the radius is not 145 megaparsecs, now you have a problem. You have to explain why not, right? And you have to start tweaking them on. All right. So we're in the regime now where we can do this over a range of redshifts, right? So not just near us, but far away from us, and redshifts of order 2. And so that's a significant fraction of the universe's observable volume that we can do this with. Okay. So in a little more detail, the thing you measure is how many, you sit on a galaxy and you ask how many pairs a distance 10 megaparsecs away, 30 megaparsecs away, 140 megaparsecs away. And so you make basically a histogram of that thing, how many pairs. And when this was done in 2005, so 20 years ago, you could see this spike. This is 100 megaparsecs, the Hubble constant is about 70. And so if I divide by about 0.7, I'll get the 140. Okay, so the measurements showed this nice spike. That's the BAO feature. Sorry, on this plot, I show R squared times the correlation function. And so this thing really goes up, but because of the R squared, when R is small, it looks like it bends down again. This is not the BAO feature. So the BAO feature is here. Okay. And then the thing I had said in the class was that if you have a delta function at a scale, and that scale is 0, then the Fourier transform of delta function is a constant. But if you have a delta function that is not centered on 0, then its 3D Fourier transform gives you sine k over k. Okay? So it gives you an oscillation. And so that means that if you take the Fourier transform of this guy, then the measurement that's most often shown is not this one, but the power spectrum, the Fourier transform. And in this one, the signal is the fact that this has slight oscillations in it. So something that's nice and local in configuration space, in Fourier space, is oscillation. Most talks about measuring the BAO feature will concentrate on this. I'm going to concentrate on this, on the real space thing. It's kind of simpler to see this just as well. Okay, so that's the feature that we're after. And the beautiful thing that's happened in the 20 years since is that we've now done surveys of a range of redshifts. And so, we can, if this axis is the distance from us as a function of redshift, so the nearby to more distant. So nearby is small co-moving distances from us. High redshift is big distances from us. For different populations of baryons, most of these are just different galaxy sizes. But because this should work for any set of baryons, even the baryons in the Lyman alpha forest, they show this shell behavior, right? They show this BAO feature, and we can map out the expansion history of the universe using these different populations. And so I like plotting it this way because often the supernovae results are shown in this format, to show the expansion history. And so now we're in the regime where with the BAO we can do the same. And make exactly the same kind of, it's a geometrical measurement. We should get the same answer. Only difference is supernovae are luminosity distance versus redshift. This is angular diameter, basically that angular diameter distance versus redshift. Okay. Okay. So you can see that there's an expansion history that can be mapped out, and as we measure with smaller and smaller error bars, we will be able to say more and more precisely if the expansion history is consistent with a model from general relativity or something else. So that's the game that's being played. Okay. But to play it, just like to play it with supernovae, you have a standard candle that must be standardized in order to play the game. So too for the BAO. Okay. The standardization is better understood, and than for supernovae. For supernovae, it's a rule, right? That people noticed that you could deal with the time to maximum. Here we know that what's happened is that the baryons were pushed for a while, then they were left, and then gravity has gone to work. And over the next 14 billion years, gravity is trying to shrink the size of the shell. And so we can ask, how much has it made the shell shrink? If it has shrunk, then the rod is no longer standard, so you need to correct for that. And we know that gravity has done something because in our local universe, we can measure that things move with speeds in addition to the Hubble flow. And so we want to be sure that those motions have not destroyed the BAO feature or distorted the BAO feature enough to give us a biased answer of the actual signal. Okay. So one of the things we do is we can run simulations of gravity going to work. So this is a simulation here where, just to highlight, we've put lots of particles of low mass in a circular shell, and gravity goes to work. And what you can see is that it totally distorts the shell because things move. But basically, the shell has the same radius. It just got more blurred out. It was a nice, thin, uniform shell before, and now it's got more blurred out. The blurring out is what this thing in the bottom illustrates. It started out as a dashed. If this was the profile across here, now it's got blurred out. It's fuzzier. But our measurement is not how thick this is. Our measurement is the distance from here to here. And so the important point is that this distance was 150 megaparsecs. This blurring out is about 10 megaparsecs. And so it's not very blurred. Okay? I mean, I should say. So it might be blurred, but it hasn't shrunk very much. Okay? So this is the sense in which the BAO is a little bit more robust or a little bit better understood than the supernovae. Right? We have a reason to believe that it should not have shrunk very much. There's a back of the envelope estimate, right? That in a universe with cold dark matter, if things are moving 1,000 kilometers per second for 10 billion years, they move 10 megaparsecs. And 10 megaparsecs is small compared to 150 megaparsecs. And so that's why the BAO feature is expected to be robust. Yeah. Okay, so it's expected to be robust. However, so let me skip this. So however, it's not as clean as it was. And so one way to think of this is you're trying to make a measurement of this feature. And if the feature is very blurred out, it means that its height is very shallow. Then you can't measure it with high signal to noise. Whereas if it was really a delta function, it would be much easier to measure its scale. Right? So there's a lot of work that gets done to standardize the rod, which means to take the particles from here and move them back onto the red circle they started. Okay? So that's called reconstruction. You're trying to move the particles back to where they came from. you're trying to massage the data, right? But in a principled way. Okay. Right. And so here's illustrating that blurring out again in the actual 2-point function, right? So it started out as this blue curve, and now it's the red curve. Okay. And so now you can see that it's clearly difficult to measure the maximum here. It's clearly much easier to measure the maximum here. And so we would like somehow to move the particles so that when we make a measurement of their statistics, we get something closer to the blue curve. All right. So that's the motivation for reconstruction. And before we get into reconstruction, I want to talk about one alternative thing you could have done, okay? Which is to ask yourself, what really am I measuring to measure the distance scale? And the kind of hand wavy way I've been talking is to say, we're trying to measure the position of this peak, because that was the thing that's like the delta function, okay? And so in practice, what do people do? Okay. So in practice, well, if you're looking for a peak in some data, you could differentiate, but we know we shouldn't differentiate noisy data, so we don't differentiate. So then what do you do? So then you fit a model, and you might differentiate the model. So then what do you fit? So what most of the field does is they will fit a lambda CDM inspired model. Okay. So that means they're assuming the cosmology lambda CDM from Planck to convert angles and distances into angles and redshifts into distances. And they're assuming the lambda CDM shape for this curve. And then they fit this curve to the measurement. Okay. And so you might worry that there's a little bit of circularity going on because you're assuming cosmology to measure the cosmology. And it turns out it's not so bad, but it would be nice to have an estimate that doesn't depend so heavily on cosmology, on your assumed fiducial cosmology. And so I wanted to try to describe that before I get into a little bit more detail of the actual reconstruction process. And so what we're really looking for is we want something that doesn't shrink very much as the universe expands and gravity goes to 1, right? So and then we want something that we can measure with, let's say, high signal to noise with relative ease. Okay, so it should not have shrunk too much, and so we don't have to do too much reconstruction. And so although I was concentrating on the peak, I now want to think about the whole feature. Okay, and I'm going to call the peak the dip, and the linear point is the midpoint between these two. And the reason for doing that is that if you run simulations of gravity in GR background, then one of the things you find is that if you look at many different times, then at early times you had a nice sharp peak. And then as time goes on, red to orange to blue to black, red to orange to blue to black, the sharp peak gets more and more blurred out as gravity moves things around. And so the peak got more and more smeared out. So this was the effect that I was highlighting before. But just as this got smeared out, the dip also got smeared out. And so at redshift 0, you have quite a smeared out BAO feature compared to what you started out. But one of the things you'll see is that the point in between is basically invariant. Yeah, so it hasn't changed much at all. Heuristically, it's because, well, you had something like this and something like this, and you made this like this, you made this like this, so in between, it didn't change. Okay, but you can, I'll be more precise about this in a second. Yeah, so, but the heuristic thing is the midpoint between these two is almost invariant. So we said maybe you should use this as the standard rod rather than the peak or the dip. So this is measurements in simulations of the dark matter distribution. In practice, we don't measure the dark matter, we measure galaxies. So as a proxy for galaxies, we measured halos in the simulations. Oh, what happened? I went through too fast. So this is the dark matter. The halos are pretty much the same as this. So it should have said halos underneath. Yeah? So the halos do the same thing. So the bias tracers, galaxies, this point here is also invariant. Yeah. It is invariant, but not, again, not completely invariant, okay? So it slightly shrinks, okay? So it shrinks by less than 1%. So this is the change in position of that midpoint when the peak position has changed by quite a lot, or the dip position has changed by quite a lot. That linear point does not change much. So it's a more robust thing because it's not changing much. And it's as easy to measure as the peak or the dip. Okay. So it's a little bit more stable to nonlinear evolution. And a little bit of reason for why. So if I think of the smearing as basically convolving with a Gaussian, if you're convolving with a Gaussian, then the Fourier transform for Gaussian is also a Gaussian. And so if I expand this to 1 minus k squared, then k squared in Fourier space is a Laplacian, because the Laplacian is 2 derivatives, del squared. So that's a k squared. So a Laplacian in real space is 2 derivatives. So a Laplacian of something that's spherically symmetric is first derivative plus second derivative. Okay, so now at the peak of the correlation function, the first derivative is 0. So that means only the second derivative contributes. But at the peak is when it's very curved. And so that means this term is not necessarily small. And in fact, that's what's happening, right? Because of the nonlinear evolution, at the peak position, the amplitude is changed a lot by the smooth. The midpoint is like an inflection point. It's where you're changing from the dip to the peak. So at the inflection point, it's the first derivative that contributes and the second derivative that is 0. And so there you have a slope, but it's not a huge factor. And so it turns out that that's why the midpoint is more stable than the peak or the dip. It's because to first order, the correction is like a Laplacian, and you're just playing with which of these derivatives matter. Okay. So that's to say, the standardization of the rod, the definition of the rod, we actually have a good feel for why you should do one thing rather than something else. Okay. All right. And then we'll say, okay, I want to be sure that when this term is 0, this term is not huge. And the way I know this term is not huge is that I can compare this term to the scale on which this term is 0. So that's roughly the midpoint. That's roughly the point of the BAO scale. So that's the 150 megaparsecs. And the rough motions were 10 megaparsecs to 100 megaparsecs, or 150. So this squared is a small number. So that's why the suppression is small. Okay. I have a little bit about, so this is more technical, so let me skip this. This is just saying, if you play this game, then you have an easy way of estimating what will be the error on the measurement. So one of the tough things that's happened in cosmology is now we have so much data. There's the beautiful physics, but then there's all the hard work statistics, which boils down to being able to quantify the error on your measurement, because we're trying to do things at sub% precision now. And so a lot of work goes into that. A lot of simulation time goes into that. And for this particular estimate, you can write down an estimate of the uncertainty on this scale that you don't need to do the big simulations. So it turns out to be very convenient. So if you're interested, ask me later. Okay. All right. The other thing you can do is you can say, well, at the end of the day, I just want to measure the shape of a curve like this. That's a cubic. And so maybe it's not going to be exactly a cubic. So I can just fit some polynomial to the data. And from that polynomial, I can infer that inflection point. Okay, or infer the midpoint between the peak and the dip. And so that means I can infer this scale without assuming a cosmology. I'm just fitting a polynomial. Okay, so it turns out that if you take a polynomial and you convolve the polynomial with a Gaussian, that is also something you can do analytically. So that means you can fit the convolved polynomial to the data. And then the fitted coefficients you can apply to the original polynomial, not the convolved. If you do that, you have done reconstruction. You've accounted for the smearing of the BAO. And so that is what's shown here. So you fit to the crosses. Okay, so you fit to the crosses, and the process of doing the fitting, you've chosen these special functions, which are just so you can fit a polynomial to the, you could fit a polynomial to the crosses, or you could fit these other functions to the crosses. If you fit the other functions to the crosses, you take the coefficients, you treat them as though they're coefficients of a polynomial, you will get this curve. And that's the reconstructed curve from fitting to these measurements. So that's a very simple procedure for accounting for the smearing that happens because of the gravitational evolution. So it turns out this works very well. Yeah? And it's extremely cheap because you're just trying to reconstruct statistics. So here it is applied to the DESI survey, okay? To the bright galaxy sample, a few of the luminous red galaxy samples, and one with the emission line galaxies. Okay? And so in all cases, you know, there are the measurements, and then you can fit to the measurements and do this kind of reconstruction. Okay? There's the measurements with rather large error bars, and then these bands are showing you the estimate on the linear point scale that you get from doing this. Okay? And so I'll take those measurements and plot those versus redshift to show you, if I take the linear point scale, I divide by this fiducial angular size that I defined before. This is like an angle, right? Because angular diameter distance times a scale gives me the times angle gives me physical scale. So now I've taken the physical scale, divide by this gives me the angle. And so the things that are far away have small angular size. This is the dotted line is the Planck model. And then the measurements are the measurements in the DESI DR1 and DR2. So you can see that they're very close to this. Okay, there's a little more detail here for people who are interested in possible departures from lambda CDM. I don't want to focus on that for this talk. Yeah? So this is just to show you that this very simple thing of fitting a polynomial gets you the cosmology without assuming lambda CDM. Okay. As a reality check, the curves on here are the much more sophisticated official DESI analysis where they did assume lambda CDM. And so if you were nervous that what they did was a bit circular, the fact that the polynomial is giving the same answer should be reassuring, right? Should say it's not too bad that they are doing something slightly circular. It's just that this way of fitting a polynomial is much easier. Okay. Okay. So this was easy, and now I want to talk about a more complicated thing. So the easy thing was just trying to talk about the 2-point statistics and how we might make the 2-point statistics look like they were 14 billion years. But we could ask, what did the entire field look like? So that if I can reconstruct the field, I can measure any statistic I want, not just 2 points. Okay? So that's going to be the next thing I talk about. And that one again, the field has a way of doing this. And I want to describe a slightly new way of doing this. And I will try to highlight what's different, okay, as we go through this. So the way I'm going to use, the method I'm going to use is called optimal transport. And so optimal transport is an old problem. So it's about, I was going to say, it's not as old. So yesterday I was in Ravine math, right? And so that's what, 1500 years, if not more, right? So this is about 300 years old, okay? The original problem, Monge was an engineer. He was trying to find the most efficient way to move dirt from one place to create a palace in a new place. And so he sat down and he said, you know, what do I need to come up with this rule? And so he said, well, I need to decide where I start from, where I have to go, and what's the cost of doing this. Okay, so those are the ingredients: starting point, ending point, the cost to transfer. And he said, well, then I want the one where the cost is minimized. Okay, just like in physics, everything is minimized. So so that's the problem. And so in this problem, you know, you have a pile of dirt, you have to move from here to here. You have another pile of dirt, you have to move from here to here. So there's like a discrete thing. Okay? The example that you sometimes use is you have a bakery that's making croissants, and the baker has to deliver the croissants. You have 10 bakeries in the city, 10 places that they are sold. What's the most efficient pairing of baker with shop? Okay. That was the problem Monge solved, or at least set up. It took a while to be solved properly. And advance came from saying, why should it be that a bakery delivers all its croissants to one and only one shop? What if each baker can deliver some fraction to different shops? And so each bakery can deliver some fraction. And this seems like a trivial step, but this step made a big difference in terms of how people thought of this. So this was the generalization by Kantorovich, not quite 100 years ago. And that generalization has led to a big boom in the use of this optimal transport framework in machine learning, in analysis statistics, probability theory, all this stuff. And so that means that a bunch of computer scientists are interested in solving this problem. And so we're going to make use of that expertise. So for us, the problem works like this. So the positions of galaxies today are the red dots. We think, because we've seen the CMB, and the CMB looks quite smooth, we think that the mass started out uniformly distributed. So that means we think the starting point were blue dots. Our problem is to assign, you know, which red dot is with which blue dot. And so the way I've drawn it, it's kind of easy. The closest red dot goes, you know, to the blue dot that's closest. But if you think a little, you know, this is a little bit fake, right? Because I could have had a finer blue grid. And if I have a fine blue grid, then how do I know which blue dot is for the red dots? Okay, so that becomes like a discreteness dominating. So how do I solve this in a nice way? And so the nice way is this way that Bruno Levy came up with, which is to say, you know, supposing I double the size of this grid, meaning I made the grid much finer, the blue grid. Okay, so now here's a finer blue grid. And I doubled the grid again, right? So I made it even finer. Okay. And so what I want is I want the set of all blue dots that are closer to the red than to any other red. Okay, that's what I want. So that's this kind of partition. Okay? And so what the computer scientists have is a very fast way of solving this assignment problem. And this is by phrasing it this way, you've now basically taken the limit of infinitely dense sampling of the blues. So you've got rid of the discreteness problem. Okay. So to try to give you a little bit of feel of what this is like, some of you will have heard of the Voronoi tessellation. So the Voronoi tessellation is you go to a point and you ask what volume of space is closer to it than to any other point. And so you partition space up like this. So that is, if you do that, then each Voronoi cell has one point in it, but each cell has a different size. And you partition space completely. This one, we want something similar but different, right? Because we want that the initial conditions were uniform. So that means we want that each point is in a cell of equal volume. The shapes can be different, but they should all be the same volume because the density inside each cell should be the same because I want a uniform initial condition. So that's the rule. Okay? And that's the thing that was hard. So fast codes to do Voronoi have been around for a while. Fast codes to do this other thing where you want Voronoi, but all the cells should be the same size. All the cells should be the same size means you do Voronoi, and now they're different sizes. So now you make the small one bigger, make the big one smaller, and you start moving around the cell because they must all touch each other's walls. And you gradually find what is the set of cells that all have the same size, each with one point inside, one red dot inside. Okay. And so that partition is called the Laguerre diagram. And so that's the code the computer scientists made. And so we took that code. Okay. If you want, here's the detail. So a Voronoi diagram is saying, I go to each point x, so xi, and I ask all the positions q around this point that are closer to it than to any other j, any other xj. That's Voronoi. And now you say, I want to do something a little different. I will add a term here. And I'm going to change this term. So this is the thing that's changing my Voronoi. And by changing this term, and each cell, each particle, if you want, I have to find these numbers that will let the cells all be the same volume. Okay, so I'm trying to find what is this number that is for this cell, that is its Laguerre cell, that makes it different from Voronoi. If these were all 0, that would have been Voronoi. So that's the game. But it turns out that this expression here, for people who do large-scale structure, this is the action in the Zeldovich approximation that when you minimize, you will get the Zeldovich trajectory. And so that means that the computer science problem of making the Laguerre cell is the exact minimize the action of the Zeldovich approximation. And so there's a real physical intuition that goes into this solution. Okay. And this is, so that means in this problem, these numbers are like a potential. Minimizing this means like taking a gradient. The gradient of the potential is the amount by which you have moved. And so this is, you're trying to find the potential whose gradients gave you the displacements that told you how far each particle moved from the beginning. Okay. So just to show you, okay. So if you start with this set of particles at redshift 0, and you run this algorithm, then you find that these particles came from a partitioning of space where, so this is a cube where one side maps onto the other, so it's really like a torus. And so this bulge here will come in on this side. So this has periodic boundary conditions, but it's not showing that. And so what you can see is that the small blobs here were actually big in the initial conditions. Yeah. And so this is mapping between taking today's positions and mapping them back to where they came from. Okay. And so just to see how well this does, here is a pretty big object. Okay. This is the blue dots are where are the particles that make it today. Those particles, they were initially these grids in a simulation, right? And the gray region is what the optimal transport reconstructed as the shape. So to show you that it does a good job of reconstructing the shape of the object, even though, so this is looking at the same object from 3 different angles, X, Y, and Z directions, even though, you know, the center of the object today is outside the region that defined it in the past. No? So the object was shrinking and moving. And so it shrank and it moved so much that it is today outside the region that it was initially, right? So all these particles shrank and the optimal transport gets that. Okay, so it does a very good job of reconstructing the field. And I'm emphasizing this because it does this on quite small scales, right? Nothing moved more than 10 megaparsecs. So the optimal transport is working on scales of roughly 10 megaparsecs. And that's much better than the scales on which reconstruction is usually done, which is 100 megaparsecs to get the behavioral figure. Okay, so that's the strength of this approach. A quick thing about exactly how it's different from the standard approach. If I thought of a shape, and the shape is going to get squeezed by gravity, so this is something that Julia and Carlo know well, right? Yeah, you have a shape that's going to shrink. If it's going to shrink, then I can write out its density today. So 1 plus how overdensities come to the background is the mass over the volume. And that's equal to, well, initially it had some size. Finally, it has a new size. So if all the mass is still inside this region, all that happened is it shrank. Then I care about how much this changed. So I can write this as the initial size times 1 minus a correction, because it shrank. So here's the 1 minus a correction, because the initial size cancels out. Okay. And so the nonlinear density is 1 over this for the correction for each of the 3 axes. It's just describing the change in the volume, because the mass is conserved. So this thing, you can expand. You can do a Taylor series pretending this thing is small, so you will get a term that is linear, then you'll get terms that are squared, then you'll get terms that are cubed, and so on. So the term that is linear, that's what people call linear theory density. When the nonlinear density is the linear theory density, but in fact, there are corrections. So what the usual procedure is doing is it's truncating this. It's saying the nonlinear density is this term and it's throwing away all this stuff. And what we are doing is we're keeping all of them. Okay. So in optimal transport, we keep all this other stuff. And that's why we can go to smaller scale. That's it. And so because of that, we can reconstruct shapes. So an interesting thing will be to try to compare these reconstructed shapes with their initial shapes. So one reason for showing this is that the long axis at late times is this way, but at early times was clearly this way. So this is one of the things that Julia had discovered 10 years ago, right? Was that the axes, the shortest axis might rotate as an object evolves. And here the optimal transport is able to recover that. And so there's a lot to be done with the reconstructed fields in optimal transport, not just doing the BAO. Okay. All right. So a quick thing about how it's cheating, and then I'm close to that. So it's cheating because, you know, really to make this object, I had all the particles that shrank and came in, and then they made a mess because the object visualized. But in optimal transport, everything is a potential flow, so nothing can cross. So everything had to be straight line motion. And so what the optimal transport is assuming is that this thing, I just, you know, trace everything back in straight lines. The particles on that side came from here, the particles on this side came from here, and there's no crossing of these lines. Which means that the displacements are okay, but not perfect, right? Because it could be that this particle actually evolved onto the backside of this. And optimal transport is not going to get that right. But that's the size of these clumps, because they shrink, the clumps are 1 megaparsecs in size, the motions are 10 megaparsecs in size, so you're making a 10% error on the actual shape. So it's not that bad. That's where you're gaining, right? That all the stuff all the mess that's happening inside a virialized structure, in the jargon, what we call shell crossed, is gone. This is treated in this simple way. Okay. All right. I'm running late, so I'll just show you a couple other things that we can do. And if you have questions, then you can ask me later. Okay, so I won't get into the details. I'll just show you that if we were to measure the 2-point function, then the optimal transport does a pretty good job of reconstructing the BAO shape down to significantly smaller scales, so scales of order 20, 25 megaparsecs than the standard way of doing things. Okay? And so it's pretty powerful. The other thing it lets you do is it lets you make a distinction between the particles in your survey, like the galaxies, and the other stuff that is lower mass, that didn't make it into your survey. And so you can start playing games with two types of particles: the bright guys and the faint guys, the massive guys and the less low mass guys. And in our field, there is a technique that's called multi-tracer. So if you have more than one tracer sitting on the same patch of sky, then you can beat the fact that you have only one sky, because you have multiple tracers in the same sky. So you gain in statistics by using this. That's something that the standard method can't do. So I will just skip that there. And the final thing is, I know that people like Mark are interested in primordial non-Gaussianity. If the initial conditions were not Gaussian, well, there was no requirement that any of this stuff was Gaussian in setting this up. The most interesting non-Gaussian initial conditions are non-Gaussian on quite large scales, for which the Zeldovich approximation will still work. So optimal transport is still a good model. And so we've tested that for those models, it works well. And so the final thing was we set this up to do a field. So we don't have to measure only 2-point statistics. We can measure void statistics, plus the statistics, plus the shapes I've already talked about. So you can do those things as well. And so I just wanted to highlight that you can do a bunch of stuff in these reconstructed fields that you could not before. And so there's a bright future. Okay. There's synergy with the kinetic SZ effect. I won't talk about that. If you're interested, ask me later. I wanted to highlight one other thing. So there's a nice coincidence, a nice thing that happens. If you write down the equation for time delay in gravitational lensing, so photons had to travel 2 paths to get to the observer, you would write the path as having 2 contributions. There's the geometrical path, and there's the time, the fact that the gravitational, the time delay path. Okay. So this has exactly the same form as the Zeldovich approximation that I wrote before, the action of Zeldovich. Okay. And so for time delay Hubble constant, you minimize this action to get this guy. And so the hint here is that optimal transport is a good language for solving this, because what's happening where there's a revolution, the Euclid satellite is going to see 100 times more of these systems that currently exist. And so being able to analyze them fast will be nice. Yeah. So this is a good candidate for doing that. Okay. So I should just I'll just stop there and say there's sort of a nice convergence of things we can do with optimal transport, and that I also talked about using the linear point, which was a much simpler way, not reconstructing the full field, just doing statistics. So sorry I went late, but I stopped there.
Yeah, I have a few case. Just in the optimal transport, I want to understand if just use position? So you feed the optimal transport with velocity?
That's a great question. Yeah.
Information. And if so, like is velocity coming from continuity equation or nonlinear velocity? So
Right. So at the moment, we don't feed any velocity. So if you want, so in a very formal sense, you can say you have 3 nonlinear positions and three nonlinear coordinates x, y, z, and vx, vy, vz. So the full phase space is 6 numbers. So if we feed it positions, that's 3 of the numbers. Can we give it 3 other numbers? So maybe we can give it the line of sight velocity. So we can give it, right? Here, what we're giving it instead is we're saying it should have come from an initial field that is uniform. And then we're using optimal transport to decide which of the uniform volume, made my coordinate. So it's a bit like saying 3 final coordinates of position and 3 initial coordinates. That's how you're doing the complete phase.
But you have an assumption there either, right?
But you have the assumption that it's all potential.
Yeah.
That it's a
And
convex
also
potential.
yeah.
Yeah, that's right. So there's an assumption. But as I tried to argue, that one is wrong on small scales. It's not wrong one, right? However, it happens that that we will be getting a bunch of kinetic SC velocity estimates for objects. And so one of the games we played was we tried to measure. So I have the velocity an object has today, and I can compare that with the velocity that it had in the initial condition to see if it got deflected. That's one of the things I can compare. So that's what was called V halo with V proto halo. So that's the yellow. So that's the 2 instantaneous velocities, initial and final. Okay. But I can also compare let's say the final velocity with the vector that describes how it traveled. So not its instantaneous velocity, but it went from here to here. So its displacement was like this. It might be that now its current velocity is like this. That's maybe its initial thing. Right? So instead of instantaneous with instantaneous, you can do instantaneous today with the integral of all the velocities from initial time to today. Because what optimal transport is giving you is that integral. Okay. So you can compare that, and what you can see is that those are much better aligned. And so what this thing is trying to show you is that for more than half the objects, so that's the 0.5, for more than half the objects, the misalignment between what optimal transport says the displacement was and what the true displacement was is costs of 0.994. So they're very well aligned. And so what we can try to do is we can start trying to use the velocity information to guide the optimal transport guess to speed up the code. Vice versa, if we instead trust the optimal transport, we can use it to guide the kinetic SC separation between the contribution to optical depth, contribution to that kinetic SC effect from optical depth versus from computed velocity. Yeah, so there's a big synergy to be had here.
There is a way to use it as an optimal transport technique, just to have a way to detect some specific object, like, for example, points of clusters or things like that.
Yeah. So that was kind of the motivation behind this picture, which was to say, so one of the difficult things in real data is that there are redshift space distortions. And so especially for voids, knowing where the boundary is, this kind of thing. And so it can be done more cleanly if you don't have these distortions. And so you now have 2 choices. You can use the optimal transport. Optimal transport gives for each object, gives velocity. give a displacement. Now you assume that the displacement and the velocity are pointing in the same direction. So then you will have an estimate of the velocity. So you have an estimate of what should be the redshift space distortion. And so you can try to use the predicted velocity information to help guide the identification of an object as being in a void wall or a cluster. Or you can say, I'm just going to do all the void identification in the reconstructed field. And so instead of working in the evolved field, at first, I'm already massaging the data back to the initial conditions to measure 2-point statistic. I'll measure all the other things in that field as well. And that one is pretty clean as well. And that one, when we checked with void finders, it was quite good. So it's something we should talk more about trying to do this. Certainly in DESI, they're interested in fact, there are papers in DESI saying it's better to do the void finding only in the reconstructed field. And so this is one way to do that.
Okay, last one. You said about the detection, the claim detection of individual BAO. There have been, so like just you get the sphere in the structure,
Okay.
right? It's been claimed that there was some detection, but it's kind of controversial.
Right. I would have thought that's tough. Right? So I would have thought that was tough. So I would have thought. So let's look at this next slide. Okay. So I have error bars on here. Okay? And the error bars came from taking an average over like a simulation, maybe about 50 simulations that are the size of the DESI. In any one, the difference can be quite large. So there's a fair fraction of simulations in which you can't even see because the actual signal is this blue curve. Sometimes the signal is completely blurred out. Okay. This was taking all the pairs, so n squared galaxies. When you do an individual object, it means you only had n. You sat on one and you counted the n others. And so the cosmic variance on that would be very big. So you have to get super lucky. And so I think that if you wanted to put a real error bar on that, you have to put the cosmic variance error bar, and now it's a tough thing to claim. Yeah. It would be great, but I would have thought it's tough, just because of the allowing for the cosmic variance. If they're highly biased, maybe.
Yeah, that does. From sit in the center of a large cluster.
Okay, so if there's another question, let's thank Ravi again. If you want to talk to him, he's sitting downstairs, 3rd floor of the ENA. Yes. Yes.
So when you said with the optimal network, you don't have to cross it. Yeah. So you're going to connect that to your final position with your initial position. Say the stuff that's on one side of an object